Okay, let's jump right into this explainer and lift the hood on a pretty frustrating chemical reality. One that's causing, well, a ton of unexplained fuel system degradation in repair shops all over the country. If you're turning wrenches for a living, you've absolutely had a vehicle roll into your bay recently with fuel issues that just don't make sense, right? Maybe it's a completely degraded fuel line on an older SUV, or a customer complaining about sudden stalling and garbage fuel economy in a mid-2000s sedan. Today, we're digging into the science behind the exact fuel your customers are pumping and why it might actually be the hidden culprit. So, why exactly are we seeing this massive spike in melted fuel lines and mysterious lean codes? Well, it really forces us to look past the scanner and focus on the fluid itself. As techs, we're trained to hunt for failed parts, a bad MAV sensor, a clogged injector, maybe a blown pressure regulator. But what happens when the part didn't just fail on its own? What if it was literally chemically attacked by the very fluid it was designed to carry? That, my friends, is the reality of E15 gasoline. We're going to take a systematic, diagnostic approach to this. First, we'll look at the rise of E15, then ethanol as a solvent, followed by the phase separation threat. After that, we'll tackle thermodynamics and stoichiometry, and wrap up with EPA rules versus OEM reality. Okay, Section 1, the rise of E15, a chemical shift at the pump. To really diagnose this, we first have to understand how our fuel supply quietly changed right under our noses. A customer rolls up to the pump and they see this cheaper, unleaded 88 sticker. To a budget-conscious driver, 88 octane for, say, 30 cents less a gallon than standard 87, that looks like a total steal. But what the pump kind of hides is that the extra octane is coming from a much higher concentration of plant alcohol. They aren't just buying cheap gas. They are buying a literal 15% ethanol and 85% gasoline blend. Driven by federal mandates and octane needs, E15 has exploded across the map. Over 4,700 stations in 34 states now. And look, this wasn't an overnight thing. The EPA started letting 10% ethanol blends slide way back in 1978. Fast forward, the renewable fuel standard pushed for way more biofuel, and then in 2011, the EPA granted a partial waiver to allow E15 for light-duty vehicles from the 2001 model year and newer. Translation: millions of vehicles are legally allowed to run a fuel their engineers never originally planned for. Moving on to Section 2, ethanol as a solvent, the internal deterioration. The absolute crucial takeaway here is the physical damage this stuff does inside older systems. Remember, ethanol is a highly powerful solvent. It acts like an invisible saboteur, just slowly eating away at legacy materials not built for high alcohol content. If a vehicle was built before advanced synthetic elastomers became the standard, this alcohol concentration actively degrades natural rubber. Plastics swell and crack. It literally oxidizes unvarnished aluminum. You guys know the drill. We've all scraped out that nasty, gummy residue and cracking open an old carb or fill rail. It's not a sudden explosion. It's this slow, creeping deterioration that eventually brings that clogged filter or leaking seals straight into your shop. And hey, these aren't just crazy lab theories. These are verified, shop floor observations from guys turning wrenches every day. Take this quote from a technician forum. He noticed oxidized aluminum and destroyed rubber components in a 2001 Cherokee and a 2008 Element. Models that technically fit perfectly right under the EPA's approved 2001 and newer umbrella, but they are still getting wrecked by the solvent effects of E15. All right, Section 3, the phase separation threat, water in the tank. Let's shift gears and talk about severe running issues. This is where E15 becomes a massive headache for vehicles that sit around. Because ethanol is hygroscopic, leaving it in a vented tank sets off a nasty chain reaction. It naturally pulls humidity right out of the air. Testing shows it takes maybe 3 months of high humidity in a vented tank to hit its maximum water tolerance. Once it hits that threshold, bam! The ethanol unbinds from the gas, grabs onto the water, and sinks straight to the bottom of the tank. So now, that fuel pump is sucking up a highly corrosive, completely non-combustible water alcohol soup. Once those layers separate, the only fix is dropping the tank, draining it, and purging the whole system. And yeah, that hits the customer's wallet hard. We've all seen those mechanic-in-a-can bottles on the auto parts shelf promising to magically fix bad gas, but can they actually reverse phase separation? Nope. Basic chemistry says absolutely not. You can't force the ethanol and water back into the gas. The octane is shot, the fuel is junk, and you're dropping that tank. Moving to Section 4, thermodynamics and stoichiometry, the energy deficit. Beyond the physical damage, we've got to look at the engine's ECM,
and how E15 seriously alters the fundamental thermodynamics of combustion.
So 30 to 33%. That is the massive volumetric energy deficit of pure ethanol compared to standard hydrocarbon gasoline. A gallon of pure ethanol literally contains about a third less energy than a gallon of pure gas. So naturally, when you dump 15% of that low-energy alcohol into the mix, the overall energy content of the fuel takes a big hit. Because E15 has less energy, the ECM is forced to continuously adjust timing and just dump more fuel into the cylinder to keep the engine from running dangerously lean. The computer reads the O2 sensors, sees a lean exhaust because the fuel is oxygen heavy, and cranks up those fuel trims. Now, for modern flex fuel vehicles, not a problem at all. But for older conventional vehicles that are already pushing the limits of their fuel trim parameters, you're going to see check engine lights and those annoying, mysterious lean codes. And the irony? The customer's fuel economy drops, completely wiping out that 30 cents they supposedly saved at the pump.
And this is a great point from another tech quit. It explains why you might be seeing crazy carbon buildup on valves. Vehicles without dedicated flex fuel sensors have to basically guess the alcohol content using O2 sensor feedback. When they guess wrong, they run rich. Add in the fact that ethanol burns cooler, meaning the carbon doesn't get hot enough to burn to ash, and you've got a perfect recipe for nasty intake valve deposits.
Finally, Section 5, EPA rules versus OEM reality, the compatibility gap. Let's untangle this super confusing gap between federal approvals and actual OEM warranties.
So the EPA legally signs off on E15 for 96% of the fleet. But from our perspective in the shop, pouring it into pre-2012 vehicles can easily void warranties and trigger catastrophic failures. The EPA says 2001 and newer is totally fine. But automakers didn't actually start designing systems for E15 or putting it in the owner's manuals until 2012 at the very earliest. And brands like Mercedes, Mazda, Volvo, they still don't explicitly approve it. If a customer nukes a high-pressure fuel pump on a 2010 car using E15, they are completely on their own. As a shop, you've got to be really careful about the liability you take on when advising on these repairs.
Even the government flat out admits that specialized and older engines just do not have the computer controls or synthetic elastomers to survive E15. It is strictly prohibited in motorcycles, boats, and small engines like your shop lawnmower. These engines use open-loop carbs and old-school rubber. If E15 gets in there, it strips the varnish, clogs the jets, phase separates, and basically guarantees you'll be rebuilding carburetors all weekend long.
So, as you head back to the bay today, keep this in mind. E15 might stretch the national fuel supply, but for millions of older vehicles out there, it's acting as a silent chemical test of endurance. Understanding the mechanics of E15, from its solvent properties to its thermodynamic works, gives you a huge edge when diagnosing these modern fuel failures. So what do you think? Is ethanol the future of fuel, or just an invisible saboteur keeping legacy engines on life support? Knowledge is your best diagnostic tool, for sure. Thanks for hanging out for this explainer, and we will catch you on the next one.